indispensable to display the basic information needed for the problem on a graph. We are taking the maximum speed to be 30 miles per hour, which is 13.4 metres per second. It takes 5 seconds to reach this speed at constant acceleration. It takes 5 seconds to reach this speed at constant acceleration. The area under this part of the graph, it takes 5 seconds to reach this speed at constant acceleration. The area under this 5 seconds to reach this speed at constant acceleration. The area under the graph is 33.5. And from this information, we get the acceleration to be 2.68 metres per second squared. To set up a mathematical model, we are taking the length of a car to be 4 units and the gap in between two cars to be 1 unit. So the overall distance between cars is 5 units. N is the number of cars, so the distance from the lights for a car N is 5 bracket N minus 1.
Oh.
N is the number of cars, so the distance from the lights for a car... N is the number of cars, so the distance... Oh my God. N is the number of cars, so the distance from the lights for a car N is 5 bracket... N is the number of cars, so the distance from the lights for a car N is 5 bracket N minus 1. We now use the SUVA equation, S equals UT plus a half AT squared, to get the equation 5. Now we have the equation 5 bracket N minus 1 equals a half times 2.68 times T squared. We rearrange this equation to get T equals the square root of 5 bracket N minus 1 over 1.34. However, we need to consider thinking time of drivers. We are assuming the thinking time to be 1 second after the person in front starts to react. Therefore, the time taken for car N to get to the front of the queue is... Therefore, the time it takes for car N to get to the front of the queue is T equals N plus the square root of 5 bracket N minus 1 over 1.34. Cool. However, if we take N to be 5, T equals 8.9. This means that we need to take into consideration the level of traffic. In peak times, the light should be on for 30 seconds, as 20 cars will be able to go through. On the other hand, in less busy times, the light should stay on for 10 seconds to let 5 cars through.
Here is a model for traffic lights at a pedestrian crossing. So we're assuming that it's just a plain straight road with one light for pedestrians. We also required to make some other assumptions. So we've assumed that the pace of the pedestrians crossing the road is 1 metres per second. They also cross as soon as the light turns red, and everyone crosses before the light. They all reach the other side of the road before it turns green.
Using the assumptions of the pace of a pedestrian, we can estimate the time we should leave the light on for red. So, according to R, the time spent on red would be the width of the road plus 1, which we allowed just to give an extra time just for safety. If no pedestrians arrive at the traffic lights, then the light would remain on green throughout for as long as possible. This is to keep the flow of traffic constant and to avoid congestion. We also need to consider the minimum time the light should stay on green if, for example, many pedestrians arrive at the lights between a short interval. We estimated the time on green using our Excel document to using the rate of cars arriving at the light multiplied by the time it takes each car to pass the light. So as showing that the time on green is G, and the rate of cars arriving at the light is alpha, and the time it takes for each car to pass the light is T.
Another example we could consider is crossroads, where going from 4 different ways would use independent traffic lights. So each traffic light would need its own time on green and red, and the time on red would be equal to the time on green of the other 3 traffic lights, plus the safety time in between us. If each of the lights were to change at the same time, the cars that go a second late could crash, which is bad.
If we didn't model traffic lights correctly, this is what would happen.
If the 2 opposite traffic lights would then be at the same time, this would speed up traffic as two different sides of the road could be going at once.
In conclusion, we found that the traffic light timing depends on the level of traffic and the level of pedestrians. The busier the roads, the longer on green, and... What? No, why is that stupid face? In conclusion, it depends on the level of traffic and the level of pedestrians. The busier the road, the longer the light needs to be on green in order to decrease the traffic. For example, when there's a vent on, the traffic light should be on for longer, or something like a Sunday, the traffic light should be on for shorter time. Nearer schools, the red light should be on for longer in order to get all the pedestrians across the road. We have proved all this by a mathematical model.
Thanks for watching.
No, just stop it.
They're all...
Stop.
The biggest one.
Stop it.
Pause and go again.
So now we have the equation. Right.
Did you look at me?
Thinking time for the drivers. We are assuming, and then you can go up, James. Ready? Not yet.
Right, let's go.
As soon as I say, we need to take into consideration thinking time for the drivers. Okay?
God sake.
And
Thank
I
you,
say
Helen.
we are